CatPhysics is on hiatus due to the fact that chemistry and biology have no relevance to physics.
Hi. So, because we have this huge hiatus and nothing to do, we decided that we would broaden our horizons with chemistry and, as previously shown, biology. So, obviously there are groups, and they are angled vertically. And there's like 1A, if assuming that I am behind the periodic table, there's 1A, 2A, 3A, or etc., etc. What are you doing?
I'm drawing. Just keep going. Gosh, I don't know what I'm doing.
Okay. So, that like number before the A can give like, it's like an indicator of how many valence electrons there are, which is extremely important because it tells you about the ions that thing can make. So like, 1A, isn't it group 1A that can get +1?
Okay.
And they thus become negative because they have one more electron.
Doesn't that mean if there's one less electron, it's positive, right?
You're right. So I guess I will let this pass. And yeah. Okay. So while those groups are really important because of that ion thing, there's one group that it doesn't work the same way, and that's the noble gases, because as a teacher of mine once said, they are Zen monks, and thusly they don't react the same way.
Is this the noble gases?
It's this one. It's the last one. Yes. Yeah. So, what else? What else do we got to do? The Zen monk thing means that like they don't interact as well, and they're just passive, and it's not really gonna affect them if you try to bond them. Let's just go from left. Well, I mean, I just talked about noble gases, so let's go from right to left. Noble gases are this very last one over here, and the ones right next to it are halogens. Okay, right here where it says Earth, those are Earth alkali metals. Alkali. And these are the alkali metals. And then obviously right here is the transition metals. And the metalloids are these things that are touching this little line right here. Mm-hmm. And then these two right here actually continue on into other little dumb things, but I'm not going to talk about that right now because I don't have to. I might as well just give out right off the bat 2 examples. Potassium chloride and magnesium oxide are both ionic bonds. And stop doing a little kick dance. I'm trying to talk to you. What was I going to say? Oh, ionic compounds are like bond together with. Well, there's two. There's 2 things. It's a non-metal and a metal, and then they just. So, you see those charges right there that our audience cannot see, but they will see. Mm-hmm. You want to slip them over. Just beep. Flip them.
Okay.
Are you guys going to show it to them again to show them how we're supposed to do it?
No, they don't get that. I'm talking right now.
So, okay. So I got Na plus 1 plus... Okay, so I got...
Na to the power of +1, aka it's really just a strong.
Yeah, it's sulfur and Na sodium. So I'm adding sodium and sulfur.
Mm-hmm.
So, sodium has a charge of 1, and sulfur has a charge of -2. So now what do I do? What do I do?
You would take this, that one, and you slide it over to the bottom of the Na.
The bottom. This goes over there.
Yeah.
And the one goes beside this.
Mm-hmm. You cross them.
Okay, got that? No.
And, wait, let me see what you're doing. So you turn around.
Malacca?
See, basically what I just said she did, where she slid that stuff over and around, and then it becomes this. And because this 1 is here, it doesn't like, it's just 1. It's unspoken. It's like, it's there. And we write it out like that. And usually this happens, but I think there's a total, like the name, it's like dependent. But,
Oh, now you want to give me the marker?
yes? I'm rubbing my eye, can I not? So the name, would be sodium sulfide. Once combined. Okay. Okay, so Lacey actually got her stuff done beforehand.
Why does one of them not have a person holding it up?
Because there's only 5 people.
Okay.
Okay, I put these little indicators here, so you know what I'm talking about. I guess we'll just start off with sublimation, which is ice going to a vapor, but there's not like ice, water, vapor. No, it goes right to it. It's like ice, vapor. And I use water basically because you could just, it's easier to tell the difference between the states. So as you can see, the molecules in ice are more uniform and compact, and they don't move around as much as with the molecules in vapor, which is the same throughout the entirety of it. The only difference between vapor and a liquid is that the molecules, well, other than obvious, is that the molecules in a vapor are more free, while the molecules in a liquid, while still free and more energetic than frozen water molecules, they still are more close. So in deposition, there is vapor to solid, which is just like a reverse of sublimation. And then you have melting, which is like ice to water. And then water to ice would be to solidify. And then vapor is water, or to vaporize is water to vapor. And condensing, think condensation on the side of a cup, is going from that gaseous state to a liquid state. And I think that's all we have on phase changes. Alright, so since we talked about water in that sublimation and deposition and all the phase changes, we'll talk about water a little bit more, considering it has another property that deals with polarity. Basically, polarity is like an uneven distribution of electrons. Oops. Okay. So, that's basically what polarity is. Okay, so since we already covered what polarity means, I bet a lot of you are wondering why when things get colder and they solidify more, they get denser, but ice floats in water. Yeah. So it's because of the hydrogen bonds, and they like keep like the molecules further apart because of those hydrogen bonds, and it becomes less dense when it solidifies in the ice. And then water. Are you done writing it all? Like,
yeah, I'm done. I'm just drawing a water atom.
A water atom?
Yeah.
Because water is an atom.
A water molecule. Excuse me.
I'm so excited Okay, to know my ice floats. Spin it around so I can talk about the universal solvent.
The universal solvent.
Right here. Okay. Oh yeah, everything else that we just said.
Okay.
So
That's a nice cup of water.
Huh?
That's a nice cup of water.
Yeah, I try. So,
I thought Monica drew that.
It's true, I have a secret.
No fun, Lacey over here.
Taste. Okay, seriously though. Okay, universal solvent. It's a universal solvent because the hydrogen atoms are the hydrogen atoms are positive and the oxygen atoms are negative. So due to difficulties, we had to be bereft of Monica for a little bit, so I'm just going to finish up the thing on the universal solvent. And it's basically everything, quote, because obviously not everything is going to combine with water, has something to cling to because it's positive and it has negative things, so that the negatives are going to like stick to the positives, and the positive things are going to stick to the negative things. So really, it's really easy to work with. Yeah, I'm done. Okay, so next up on this list is solutions in solubility. And could you turn that around? Please don't hit me in the face. As you can see, unsaturated things. What are you doing?
I was sitting on my jacket.
Unsaturated things have little to nothing in them, while saturated things have like it's like sweet tea, but you don't have so much sugar that it sits at the bottom, because that's
sweet tea.
because that's super saturated. Regularly, like, saturated things just have, like, a good amount in them. And then, blah, 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 blah. For gas solubility, the things that are important are both temperature and pressure, because the higher the pressure, the higher the solubility rate. And then the lower the temperature, the better it is. So the hotter it is, the worse the solubility is going to be. Like a hot soda, it's just gross. And then did you just smack me?
I didn't mean to touch your
So
butt.
on the graph, as you can see, I redrew it. I just didn't label because the numbers, because it doesn't really matter. But for CaCl2, the hotter it gets, the higher the solubility, and it looks like it's like really soluble. And then in KCl, it gradually goes from like a 30 to like a 60 solubility, while percent of solubility in water, while the temperature grows. So you would read it as like at a diagonal. So the further the hotter the temperature is, usually things will go up as shown in the graph. But some things like Ce2SO43, it like reaches an asymptote. Yeah, that one's